Good morning. In this video, you're going to learn about basic mechanics, dynamics, and Newton's laws of motion. This is in courtesy of New Jersey's Science and Technology University's Physics Department. The laws of motion. In this presentation, you're going to learn about Newton's first law, force, mass, Newton's second and third laws, and then some examples. Okay? When we say dynamics, it describes the relationship between the motion of objects in our everyday world and the forces acting on them. The language of dynamics. Force, it is a measure of the interaction between two objects, pull or push. It is a vector quantity. It has a magnitude and direction. Your mass now measures on how difficult it is to change object's velocity. Forces. The measure of interaction between two forces, we have your pull or push. Vector quantity. Your force now is a vector quantity because it has a magnitude and direction. We have two types of forces. We have your contact force and field force. For your contact force, it is result from physical contact between two objects. Okay? As you can see on your right, we have the contact forces figures for A, B, and C. For your letter A hand is in contact on the expansion or contraction of your spring. Then for your letter B, a hand is pulling a cart carrying a baby. And then for your letter C, there is a contact force between the athlete and the rugby ball. Okay? For your field forces acts between disconnected object. It is also known as action at a distance. As you can see on the rightmost figure on your slide, we have your lighter mass about to be in contact with your heavier mass. This is in application of your impulse and momentum, determining whether both bodies are in elastic or elastic collisions. For letter C, now we have your attraction between two charges, your negative and positive charges. And then for your letter C, we have the attraction between two magnets. Okay? Either they are going to repel or not. We have different types of your forces. We have gravitational force, Archimedes force, which can be seen in your buoyancy. We have your frictional force, movement of bodies in smooth or rough planes. We have your tension force, which is applied on your strings, ropes. Then we have your spring forces applied on springs and bodies. Then we have your normal force, which is usually equal to the weight. But this is case-to-case basis. Your normal force would be equal to your weight or mass times gravity of a block if it is in an inclined or flat plane without any tensions acting on it. So we have the vector nature of force. Again, your force now has a magnitude and direction. Your net force is equal to the summation of forces. Okay? You must use the rules of vector addition to obtain the net force on an object. Okay? How are you going to get the um, net force of an object? The net force of an object is applied through which your Pythagorean theorem of your forces. As you can see here, we have your F1 and then F2. For your F2, this is your horizontal forces, and then your F1, this is or this could be your summation of forces with respect to your y-axis or vertical axis. So your resultant force or force net or net force would be equal to the square root of both forces squared, okay, as F1 squared plus F2 squared. Then to determine now the resultant angle, okay, you're going to use arctangent of your what? Your vertical force all over the horizontal force. Let's state your Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. An object at rest remains at rest as long as no net force acts on it. An object moving with constant velocity continues to move with the same speed and in the same direction, the same velocity, as long as no net force acts on it. Okay? For your Newton's first law, summation of forces is usually zero. This is applied for constant velocity problems, objects at rest. When forces are balanced, the acceleration of the object is zero. Okay, as you can see, object at rest, your velocity is zero. Hence, your A or acceleration is equal to zero. Object in motion, your velocity is not equal to zero. And A is equal to zero. The net force is defined as the vector sum of all external forces exerted on object. If the net force is zero, forces are balanced. When forces are balanced, the object can be stationary or move with constant velocity. So we have the following quantities. We have your inertia and mass. Your inertia is a property of objects to resist the changes in motion. Then mass is a measure of the amount of inertia. Mass is a measure of the resistance of an object to changes in its velocity. Usually your mass is equal to what? Weight all over your gravity. So mass is an inherent property of an object with scalar quantity of SI unit kilograms. So we have your second law of Newton's motions. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. A summation of forces is equal to mass times acceleration, or your acceleration is equal to summation of force all over mass. Okay? The SI unit for your force is equal to 1 Newton or 1 kilogram meter per second squared or 0.225 pound force. Okay, take note. The pound here in US customary unit is in pound force. You must be certain about which body we are applying it to. Okay, Fnet must be the vector sum of all forces that act on that body. Okay, only forces that act on that body are to be included in the vector sum. Net force component along an axis gives rise to the acceleration along the same axis. Your F net of x is equal to mass times acceleration at that x-axis, whereas your F net of y is equal to mass times acceleration of that y-axis. One or two forces act on a pack that moves over frictionless ice along an x-axis in one-dimensional motion. Pack mass is m is equal to 0.20 kilograms. Forces F1 and F2 are directed along the x-axis and have magnitude F1 is equal to 4.0 newtons and F2 is equal to 2 newtons. Force F3 is directed at an angle of 30 degrees and has a magnitude of 1 newton. In each situation, what is the acceleration of the pack? Now, as you can see on the diagram here, the free body diagram of your letter A, your F1 is being acted horizontally, okay? Then your F2, as you can see here, is acting opposite of your F1, and then your F3 on C or part C, we have your third force acted in an angle. Okay. Simplifying now the diagram, we have the point here or the dot here as your path. Your F1 is going to your right. Then your F2 is going to your left here for letter E. And then for letter F, your F2 is towards to your left and F2 towards your left. And then your F3 is acted in an angle towards your right. Okay. Your F net of x is equal to mass times acceleration at x, okay? So F1 is equal to mass times acceleration AX. For letter A now, to determine your acceleration X, you have to divide your F1 with your mass, or manipulating this formula here gives us 4 newtons all over zero point 0.2 kilograms as your acceleration be equal to 20 meters per second squared. How about letter B? Your letter B, if we're going to sum your forces with your x-axis, okay, force is going to the right would be positive, and forces going to your left would be negative. So as you can see here, yeah, F1 minus F2 is equal to mass times acceleration at the x. Okay, your AX gives us, manipulating the whole formula, F1 minus F2 all over M. So plugging in the values gives us 10 meters per second squared. How about for letter C? Okay, this is a little bit complex. Okay, to determine now the summation of forces at the x-axis only, okay, F3x, to determine the x component, okay, your F3x must be equal to your F3 cosine theta. So how did we get that? Your F3 here is actually the hypotenuse subtended with an angle of theta. To determine now the Fx here, okay, we're going to use trigonometric identity cosine. Okay? The component, x component of your third force becomes F3 cosine theta. Okay. Now, to further simplify the equation, to determine your acceleration at the x-axis for letter C gives us F3 cosine theta minus F2 all over M. Okay. Plugging in the values gives us negative 5.7 meters per second squared. Now we have your gravitational force. Gravitational force is a vector. It is expressed by Newton's law of universal gravitation. Your Fg is equal to G, multiply it with the mass of an object times the mass of the Earth times the radius of the Earth. Okay, your G here is the gravitational constant of the Earth. Okay, the direction of your gravitational force is actually pointing downwards. Now, the magnitude of the gravitational force acting on an object of mass m near the Earth's surface is called the weight. Your weight is calculated by mass times the gravitational acceleration. Your G can also be found in the law of universal gravitation. Weight has a unit of newtons as well. Okay. Now, to further explain this one, if we're going to simplify the value of your gravity here, okay, have your gravitational constant multiplied with the mass of the Earth all over the radius of the Earth gives us 9.8 meters per second squared for the gravitational constant of planet Earth. Okay? But if you're going to notice here, your weight depends upon the location. On your right side of the screen, it shows here a diagram of the Earth with the radius as 6,400 kilometers. A normal force. Force from a solid surface which keeps object from falling through. Okay? Hence, your normal force prevents the object from falling. Direction always perpendicular to the surface. Take note, your normal force is always perpendicular to the surface. Perpendicular to the surface. Magnitude depends on the situation. Now, on this diagram of this simple block atop from a table, okay, your block now has a weight and a normal force. Okay? The normal force acted here is from the table. Remember that your normal force is always perpendicular to the surface. Okay? So it's upward. How about if your block is an inclined plane? So how are you going to determine the normal force? The normal force is actually diagonal, okay? Since because the surface is inclined. Okay. Now Let's focus again on this diagram. On this part, you will see the free body diagram of the block. Your thermal force is pointing upwards, while the weight of the block is pointing downwards. Now, if we're going to determine the y component, summation of y component of the forces through second law, okay? Here on the Fnet, we're going to sum the forces as your normal force minus force of the block or Fg, okay? Weight of the block would be equal to the mass of the block multiplied with the acceleration at y component. And then further simplifying the whole expression gives us your normal force is equal to mg. Okay? Now tension T. So we have the force as T, which refers to tension force. Its out rope exerts forces on whatever holds its end direction, always along the cord. Magnitude depend on the situation. Okay. And I repeat, usually tension holds an object. Okay. In this diagram, all of the tension would be equal to T1 is equal to T is equal to T2. Okay. It's like tugging out of forces. Newton's third law. If object 1 and object 2 interact, the force exerted by object 1 on object 2 is equal in magnitude but opposite in direction to the force exerted by object 2 on object 1. Okay? F on A is equal to the tension on F on B. But remember this part, you're going to consider the absolute values of the forces. But if we're going to further simplify Newton's third law, remember, your force on A, okay, is equal to negative force on B. Okay? Equivalent to saying a single isolated force cannot exist. As you can see in the diagram, or F12 may be called the action force, and F21 is what? Your reaction force. Actually, either force can be action or the reaction force. The action and reaction forces act on different objects. As you can see here, we have your cantaloupe, see, supported by the table. Then we have your cantaloupe. The force is, or the weight of the cantaloupe is acted upon on the weight or force on the earth. Okay? Here, F of G is equal to the gravitational acceleration multiplied with the mass of the object times the mass of the earth all over the radius of the earth. Okay? Further simplifying the terms, Fg is equal to mass of the what? Mass or this one, the whole quantity here is the weight of the whole cantaloupe. You're going to equate it with the mass times the g all over m all over r squared. Okay, your Fg here is equal to mass times acceleration is equal to m multiplied with g all multiply it with your m all over the radius squared. Okay. The free body diagram, the most important step in solving problems involving Newton's laws is to draw the free body diagram. Okay. Be sure to include only the forces acting on the object of interest. Include any field forces acting on the object. Take note, this one, your third bullet. Include any field forces acting on the object. Do not assume that the normal force equals to the weight. Okay? This is case-to-case basis. As you can see on your diagram here, there is a um, comparative or comparison comparison between your physical picture and the free body diagram. This is the um, visual aid for physics, okay? So we have the hints for problem solving. First, read the problem carefully at least once. Draw a picture of the system, identify the object of primary interest, and indicate forces with arrows. Label each force in the picture in a way that will bring to mind what physical quantity the label stands for. Draw a free body diagram of the object of interest based on the labeled picture. If additional forces are involved, draw separate free body diagram for them. Choose a convenient coordinate system for each object. Apply Newton's second law. The x and y components of Newton's second law should be taken for the vector equation and written individually. This is often results into equations and two unknowns. Okay? Solve for the desired unknown quantity and substitute the numbers. Usually, F net at x is equal to mass times acceleration at x. F net of y is equal to mass times acceleration of y component. Objects that are either the rest or moving with constant velocity are said to be in equilibrium. Okay? Objects that are either at rest or moving with constant velocity are said to be in equilibrium. Okay? Acceleration of an object can be modeled as a is equal to zero. Okay? This is actually your first law of Newton's. If summation of forces is equal to zero, considering the x components of those forces would be equal to zero, as well, those forces at the y component would be equal to zero. A lamp is suspended from a chain of negligible mass. The force acting on the lamp are downward force of the gravity, the upward tension in the chain. As you can see on the diagram here, the tension is upward and then the downward force here is the weight of the lamp. Applying the equilibrium gives us, since this is stationary, you're going to use Newton's first law of motion. Summation of forces would be equal to zero. For the summation of forces, we have T minus Fg would be equal to zero, or your tension now would be equal to your weight of the lump. Okay? And then we have another example for your first law of motion. A traffic light weighing 100 newtons hangs from a vertical cable tied to other cables that are fastened to a support. The upper cables makes angles of 37 degrees and 53 degrees with the horizontal. Find the tension in each of the three cables. Conceptualize the traffic light. Assume that the cables don't break, nothing is moving. Okay, nothing is moving, so you're going to apply here what? First law of Newton's motion. Okay, to categorize now, no movement, so acceleration is zero. Model as an object for the summation of forces at x would be equal to zero and f of y is equal to zero. Okay? To further expand your solution, okay, you're going to determine now summation of forces at y would be equal to zero. Your tension 3 here, you're going to assign tension 3 or T3 here, okay, minus the weight of the traffic light would be equal to zero. Hence, your third tension here be equal to 100 newtons. How about the other tensions? We have your T1 for 37 degrees, okay? And then second tension or T2 for the 53-degree angle cable, okay? First is to determine the summation of forces with respect to the x-axis. So we have this one since um, both forces, okay, are coming from the cables only. So T1x plus T2x is equal to negative T1 cosine of 37 degrees plus T2 cosine of 53 degrees. And then, since this is first law of motion, you're going to equate the following quantities to zero. And then we have your summation of forces with respect to the y-axis. So Fy is equal to T1y plus T2y plus T3y. Hence, simplifying or further expanding the components, the y components of the forces, we have T1 sine 37 degrees for the first cable, T2 sine 53 degrees for the second cable, and minus 100 newtons. Okay? Further simplifying the following terms, T2 gives us T1 multiplied with cosine 37 degrees all over cosine 53 degrees. Or it's simplifying the whole terms gives us 1.33 of T1. Now substituting the values gives us T1 is equal to 16 newtons and then T2 is equal to 1.33 multiplied with 16 newtons gives us 80 newtons. Hence, your first tension or your T1 for the first cable, okay, that is 16 newtons. And then for the tension on the second cable gives us 18 newtons. And for the third cable, which was solved earlier, gives us 100 newtons. Okay. Acceleration, accelerating objects. If an object that can be modeled as a particle experiences an acceleration, there must be a non-zero net force acting on it. Draw a free body diagram. Apply Newton's second law in component power form. Okay, repeat. For accelerating objects, okay, you're going to consider Newton's second law of motion. Hence, the summation of force is equal to mass times acceleration, and then summation of forces at the x would be equal to mass times the acceleration at the x component, and the summation of forces, the y component, would be equal to the mass times acceleration at y component. A man weighing himself with scale in an elevator. While the elevator is at rest, he measures weight of 800 newtons. What weight does the scale read if the elevator accelerates upward at 2.0 meters per second squared? Okay, so how are we going to solve this one? To solve this one, okay, the summation of forces Fy is equal to normal force minus your weight would be equal to your mass of the elevator plus the man multiplied with the acceleration of the elevator going upwards. Okay, now simplifying the whole terms, your normal force is equal to mg plus ma. Okay, or m multiply it with the gravity plus the acceleration of the elevator. So plugging in the values gives us n is equal to 80 multiply it with 2 meters per second squared plus the gravitational acceleration 9.8 gives us an answer of 624 newtons. Okay, to determine now the weight, okay, or the mass. Mass now is equal to weight all over gravity, okay, 800 newtons all over 9.8 meters per second squared, or 80 newtons. Okay, hence your normal force N is greater than the weight. For downward force, um, since this is downwards, your acceleration becomes negative. So 80 multiply it negative 2.0 plus 9.8, that would be equal to 624 newtons. Okay, so your normal force is larger than the mass times gravity. Yeah. So that concludes my presentation for dynamics, okay, and basic mechanics. To sum it up, for bodies at rest or constant velocity or non-accelerating objects, you're going to sum your forces to zero. While for accelerating objects, you're going to sum your forces, mass times acceleration.